Hi, welcome back to AP Chemistry. You're here with Mrs. Mays, and we're going to study bonding and molecular structure in this unit. So we'll be starting off with why and how bonds form between atoms, and then apply periodic trends to justify the types of bonds that might form: ionic, covalent, polar covalent, and so on. We'll also be looking at how we calculate the lattice energy in ionic bonds, and calculating the bond energy in covalent bonds, which has a slightly different twist to it. We'll also sketch the most stable molecular structures of compounds and figure out how do we predict stability, and apply VSEPR theory then to predict the molecular shape of the structures that we sketch. All right, let's start off with forming bonds. What is a bond anyway? Well, bonds are simply forces that hold atoms together, and it's all based on the same principle as what holds things together in real life, like duct tape and scotch tape and glue. It's electrostatic attraction that holds things together. The fact that there are positive charges and negative charges that are an inherent property of matter, that is what holds things together. Electrostatic attraction. So the bond energy describes the energy that's required to break a bond between atoms. In other words, we have to overcome the attraction of a positive nucleus for a negatively charged electron in another atom. Why do compounds form? Of course, it sort of takes energy to put them together, right? To form a bond, it requires energy. Well, we form compounds because it gives the system the lowest possible energy that it could be at. So it stabilizes the entire system to form these bonds. If it doesn't stabilize the system, then it's not going to form the bonds. So the thing that holds the universe together is electrostatic attraction. And in our last unit, we looked at Coulomb's law describing the electrostatic force between charged particles. This time I want to look at the energy, and I'm not going to go through in physics how we go from force to energy, but notice again we have Q, where Q is the charge, R is the distance between the centers of the atoms. Remember, what's at the center of an atom? Right, a positively charged nucleus. And if the charges are opposite, like one of these is positive and one of these is negative, then the energy between them is going to be negative, right? A negative times a positive gives us an overall negative charge. So if you have a nucleus, a positively charged nucleus, and you have a negatively charged electron, then that energy is going to be exothermic. But if your particles have the same charge, like we're describing the energy between two electrons that are coming in close contact with one another, then the negative times a negative makes a positive energy, and this is going to be endothermic. It requires energy to put two similar charges close together. It requires energy to bring them towards one another. Ionic bonding is considered to be the transfer of electrons to form a bond. So an atom that has a low ionization energy is going to react with an atom that has a high electron affinity. So one thing wants to get rid of the electron, the other thing wants to have more electrons. And that's how we would get opposite charges. The thing with low ionization energy will form the positive charge. The atom with high electron affinity forms the negative charge, and they stick together because opposites attract. But covalent compounds, which are typically made of nonmetals, result when electrons are shared between atoms. So the sharing of electrons is how we form covalent compounds. You see, the electrons in each atom would be attracted to the nucleus of the other. Electrons are not monogamous. They don't know which nucleus is theirs to love, so they're attracted to any nucleus that has a positive charge. But the problem is the electrons that are already there around the atom sort of push them away. So what ends up happening is that they have to find the exact right balance, because the electrons, when they get too close, push away. If the nuclei get too close, they push away. But the electrons on one atom are still attracted to the nucleus on the other, so they're going to pull together only to a certain point. So they reach the exact distance that has the lowest possible energy. And that's called our bond length, when they get just to that right spot. They hit just the right balance. Again, that distance is called bond length. So let's look at this more in depth. So I have atom number 1 and atom number 2, and they are going to approach one another and get closer. Here's my atom 1 and my atom 2, and then they get closer, and then if they get any closer than this, the energy increases, because now we have repulsion for the electrons of one atom to the electrons of the other, and the nuclei begin to repel one another also. And so that's too close. They got to back up a little bit and get to exactly the right spot. So I've marked that spot here. The internuclear distance right at that spot is called the bond length, and the amount of energy that corresponds to that distance is called our bond energy. So right there, that's where the electrons are all happily attracting towards the nuclei of the other atom, but not repelling each other too much. So here's an example to show how two hydrogen atoms might interact. Notice here the electron densities are so far away that they're not even having any influence on one another at all. The atoms are sufficiently far apart so that they have no interaction whatsoever. Now, this isn't to show that a hydrogen atom has so many electrons around it. It's just all the possible places where the electrons could be. This is our electron cloud, we call it, right? But as these two atoms approach one another, the electrons from atom number 1 are being pulled towards the nucleus of atom number 2, and vice versa. The electron cloud around atom number 2 feels an attraction for the pull of this positively charged nucleus on atom number 1. When they move closer together, these atoms interact. And then finally, when they get to the optimum distance, where they're exactly the right distance between these two atoms that they can make a bond and the electrons don't repel too much, but they remain attracted, this is its most stable, energetically speaking, position to be, then we have the optimum distance to achieve the lowest overall energy of the entire system for both of the atoms in the molecule. So the distance between the two nuclei of the atom, between the centers, that's considered to be our bond length when we're at that lowest possible energy, our most stable place to be. There's one more type of bonds that we rarely talk about in regular chemistry, in general chemistry, but it turns out to be rather important in materials chemistry, because a lot of what we work with in the material world has metals in it and alloys or mixtures of metals. Metallic bonding works by a model called the sea of electrons. You see, if you have a metal, then there's a positive charged nucleus, and then there are electrons around the nucleus that don't know really which positive charge they belong to, so they are very mobile. They get to move freely around all the nuclei at the same time. And the mobile electrons in a metal tend to create what we call a sea of delocalized electrons. That's important to know, that they are delocalized. That means they just don't stay put. This is what makes metals good conductors of electricity and of heat. It also makes them very malleable and ductile. That means we can bend them around into shapes without the charges repelling one another so much that they just break apart entirely. So the sea of electrons is our model for metallic bonding. Now, I don't want to give the impression that you only have certain types of bonds available. It's either ionic or covalent. Well, that's absolutely not true. Ionic and covalent bonding are the two extremes. That's at the far ends of the spectrum. In truth, there's more of a sliding scale. We describe bonds as having high ionic character or low ionic character. In between, we would have something in the middle called a polar covalent bond. Polar covalent bonds are those where electrons are not shared evenly between the two atoms. One end of the molecule then ends up to be slightly positive, and the other end is slightly negative. And we show that when we write the small Greek letter delta that looks like a sort of curvy letter D or a squiggly looking S. But delta, we would put like a delta minus for a negative end and a delta plus for the positive end of the molecule. So let me show you an example of a very polar molecule, hydrogen fluoride. So in its gaseous form, hydrofluoric acid is just called hydrogen fluoride until it dissolves in water. Since the fluorine atom is very electronegative, its electronegativity value is 4.0, it's going to take more electrons, hold the electrons more than the hydrogen that it's sharing its electrons with. Its electronegativity value is only about 2.1. So the difference between these two, we just subtract. Difference mathematically means subtract, right? The difference between the two electronegativities is 1.9. Well, technically, anything greater than 1.7 is considered to be ionic. The difference is more than 50% ionic in its character, but it also has high covalent character. The electrons are not evenly shared between these two atoms. So what we would notice when we put these in the presence of an electrical field or in a magnetic field, they're going to align themselves. So here's our random assortment of molecules. Now let's apply an electrical field to these molecules, and notice how the molecules line up so that the negative end of the molecule is facing the positive end of our electrical field, and the positive end of our molecule is aligned with the negative end of the electrical field. If these were non-polar covalent bonds, then this molecule wouldn't line up this way. They would stay in their random shape.